yet quite reached the main sequence even. And then there's the old ones where these are the red giants and so forth. So this is the sort of thing one can do with these kind of data. Finally, this slide. This is white dwarfs here, and it matches the models. You can see it's very good the models and the actual white dwarfs here. There are white dwarfs that are actually crystallized. So these stars are solid diamonds, for whatever it's worth, because they're crystallized carbon and oxygen. Okay, so let me turn now. Most of what has been done with Gaia so far has been to map out the halo and the thick disk of the galaxy, but it's a little harder to work in the galactic plane because, of course, we have the obscuration, the extinction of the dust of the galaxy and so forth. So, in fact, in some sense, the Gaia project, being an optical telescope, it may, in some sense, is not the ideal for mapping the galactic disk, but nevertheless, there are some things. And there are some of the key problems that interest me, at least, at the moment, are the question of the distribution of stars in the galactic plane as a function of chemical composition and location within the galactic disk, the chemical history of the disk of our galaxy. I think that these pictures I just showed you show that there really needs to be more that we need to learn about the relationship between the formation of the galactic halo and the disk itself. There are still many questions to be answered here. How did we get stars into the disk and how did it develop as it is? And in fact, something that interests me is the question of the outer parts of the disk of our galaxy. And we can't see very well from here because we're in the middle of it. But to some extent, the outer parts of our galactic disk are still forming. All those star streams and so forth are beginning to land on the disk of the galaxy and are causing it to develop. And the focus of my own research is really, somebody maybe can't see too far down there, is the ages of stars, and that's what directly interests me. So let me turn to that question. So how do we find the age of a star? If you looked at a single star somewhere out in the galaxy, a single main sequence star, you really can't tell its age very well. It's a difficult thing to do because the sun, 4 billion years ago, the sun was almost the same as it does now, of course. One of the standard ways of doing it, of course, is to fit, as they say, theoretical stellar models, isochrones, models of star clusters of different ages, to fit somehow or other one of these curves to an observed star cluster. This is data I took at that Discovery Channel telescope I showed you a picture of a little bit ago. But here's the cluster here, all the way down here. These are all field stars that have nothing to do with the cluster. But how do you decide which of these matches that? And to be quite honest, what people have done, quite literally, is to just take that picture and slide it across this picture and look to see what matches the best. That's quite a primitive, thing to do, but in fact, it works pretty well, except that you don't really know, you can't be sure whether that model is the right one or that model is the right one, because they look almost the same. And you don't get any measurement of the uncertainties of your measurement. So, in the modern world where we really like to learn these things, we need to do something more. People have tried various things, but I decided a few years ago that I really wanted to learn some modern mathematical analysis techniques. And so I tried to learn a little bit about Bayesian analysis, Bayesian statistics. And I think this is becoming the old traditional statistics where you take a function and fit it to data is now often called frequentist statistics. You look for the take a particular model and fit it to the data, and you get the standard deviation and that kind of thing. With Bayesian analysis, which requires, of course, computer technology, you can fiddle around and find what's the most likely, and techniques in a much better way. And here's Bayes' theorem. How many of you know, maybe I'm preaching to people who already know, how many of you are actually familiar with Bayesian statistics? Yeah, that's more or less the way it is these days. But if you go in and read the Astrophysical Journal these days, you'll find lots and lots of people talking about that. So here's Bayes' theorem. There was a guy by the name of Bayes. There was an English minister about 300 years ago. It was a very old hypothesis, actually. And the P's there and the L, these are distributions, probability distributions. And so what it says here, the terminology with this line here means that this is a probability distribution that you will get a particular model given a set of data. That's what we're looking for. What's the probability of the various models given a set of data? And what Bayes said was it is part of these terms here, where this is the probability distribution of the models. In other words, all the possible models that you might have, you might want to fit to this. Okay, the distribution of the values of those models. Things like the distances, ages, compositions, and interstellar edging, and so forth. Okay, the range of possibilities of those, that's the model. And this is the probability distribution of all possible data sets. You go out and you make some measurements, and you get a set of things. You go out again and make a new set of measurements, you're going to get different answers. And if you make an infinite number of these measurements, which you can't do, you come up with this distribution. So in fact, generally, we don't know that. But it's a fixed quantity. So what we're going to end up with is this distribution up to a constant. So we usually ignore this part of it, although there are situations where you can use it. And then you have this term here, this likelihood, is still another distribution. The likelihood that you'll get the data given a set of models, given a particular model. And that you can make evidence of and distributions of. And so you can say, well, if I try this model, what's the data going to look like? Okay, so you can set some limits on this, and so you set distributions of the various input variables, and you do this calculation for many, many input models to see how it matches up your data. Okay, so given a model, how does it fit to the data is what we get. And you get something like this. For each of your parameters of your model, you'll get a distribution. And here's the histogram. Here is the actual distribution that you get. You do this many, many times. See, this is the number of trials. You try it. So I've tried 7,500 trials. So you take this and you go into the computer and you adjust your trial parameters just a little bit and do it again and see which is better. And you get a distribution of values and see how that compares, and then you can fit a function to it, and you get a peak and you get a standard deviation. So you get an error estimate and you get a value. Now, if you just do this for every possible one, you could go on forever, of course. So there are tricks to how you do that in practice. And one that's very commonly used with something with this fancy name of Markov chain Monte Carlo analysis, MCMC. And the way that works is you develop a suitable definition of your likelihood parameter, the L in that overlay. And you get a trial model, a given age and chemical composition and distance, or say, of your clustering, and see how well the data fits to that. And so you get a solution to that. And then you try it again by changing the model a little bit, changing your values of your distance and so forth. And if the new solution is better, we accept the new solution. If it's not better, most of the time we throw it out and try a new solution starting from the trial model. We're always starting from a particular trial, we make a small adjustment to the trial model and see if it's better or worse. But sometimes what you do, according to how much worse it is, you may accept a trial model even if it's a little bit worse. Okay? The idea is to wander around through the possibility of the space of your parameters to see how often you end up back at the same values or similar values. And you do this, see, I'm up to 10,000 trials here in this particular thing. And typically you throw away the first few thousand because you haven't done enough to get it randomized yet. And so this, I'm apparently searching for EV minus the interstellar reddening. This is the differences in the value of the interstellar reddening I get for each trial. And you see it wanders back and forth, but it's concentrated around a particular value with some distribution. And that's the curve we saw in the last one. And this means you've got a quantitative, starting from basically just your assumptions about what the model should be, which you do anyway. You end up with getting a statistical estimate of how what the best values are. And you come up with a fit here. And this is my one case of doing this, of course. A cluster, star cluster, open cluster called NBC 6811, which is in the field of view that the Kepler spacecraft had. And among other things, this particular cluster, we now know has a couple of planets around a couple of stars in it. That was some of my colleagues who did that part of it. And we fit several parameters to it. Now, so we had 4 parameters: the reddening, the distance modulus, the age, and the metallicity. So of course, we needed at least 4 kind of data. So we had 4 color indices, and I had the standard UBVRI type standard colors, and these were theoretical models from Yale and Padova in Italy. And I came up with, here's my best estimates of the value of this cluster. And here's the theoretical isochrone that fit that. And so there we are. Now, is that the right answer? Well, I don't know. It's the right answer within the assumptions that I started with. Of course, that's one of the things one has to keep in mind when doing this sort of analysis. But I now have an age of 1 billion years for that star cluster. Quantitative estimate based on modern models with a reasonable uncertainty to it. All right, so let me go in a different direction. I'm still interested in ages here, but I'm going to take a different approach to doing that. And this is now the Kepler data, where we've been mapping the stars for a long time. This is a picture of the sun, of course, with its sunspots. But other stars, of course, have spots as well. Some of them much larger spots than the sunspots are in the sun. But because the Kepler spacecraft was able to get such precise measurements of magnitudes, as a star spot group like this rotates around to the backside of the sun will change. In the case of our star, our sun, it changes by almost 0.1% over the course of the solar cycle. Just about that. The sun doesn't really vary very much. A lot of stars vary more than that. But to do this day by day over years, well, 30 days, of course, just to get to one rotation of the sun, but in order to build up the statistics, it would be very bad, very hard to do. But Kepler, of course, was able to do this. And so we now have rotation periods for thousands of stars in the Kepler field. And K2, by the way, I don't know how many of you are familiar with this spacecraft, with this mission, but the Kepler mission was a satellite, as I said, was pointed in one direction. But after 4 years, one of the gyros failed, so it was no longer able to point precisely. But some clever engineer figured out that if you pointed the spacecraft, oriented it so that the telescope pointed along the ecliptic plane at an angle of 90 degrees to the direction of the sun, that you could use the pressure of sunlight on the solar panels to help stabilize the spacecraft. So they were able to point 90 degrees from the sun for 3 months, then they'd rotate it around and point to a different place for 3 months. So they finally did, I think they did 18 of them, and it finally died about 3 weeks ago. The spacecraft, I think they ran out of fuel, but they had to move it, they ran out of fuel finally, just a few weeks ago. So they've done this now for a bunch of other fields, except each one of these other fields, they only got for 90 days. So it's not quite, but there's a lot of that. At any rate, so we now have the rotation periods for these stars. But way back in 1972, a guy by the name of Skimanich figured out from looking at a few nearby stars and a couple of young star clusters like the Pleiades and Hyades, and also the sun, our own sun, where we know the rotation period, he derived or postulated that the rotation period of a star like the sun varies as the age to the 1/2 power. And so that means that in principle, if we could measure the rotation period of a star, we could use this law to get the age of the star, a main sequence star this would be, a star like the sun. And so this seems like quite a interesting thing to do. And there have been detailed models and modeling the magnetic fields and so forth on stars, particularly a guy by the name of Barnes, who invented this idea, well, I'll come to that in a moment, studied the spin down. What he found was that you can start with the formation of a star like the sun. You have a T-Tauri star with these fantastic magnetic fields and huge flares and all that sort of stuff. And typically they're stars like the sun, when they're first formed, they rotate with a period of around 1 or 2 days. It's a typical period for very young stars. And they rapidly spin down because of the magnetic field, of course, there's a tremendous stellar wind, and the stellar wind flowing out from it carries away angular momentum, and so the star loses at least the outer layers of the star. We don't know about the interior so much yet, but it loses angular momentum and spins down. That's the physics of what's going on here, the simple physics. Except we come back to magnetic fields again, of course. And so the question is, can this be used as a practical matter to derive the ages of stars? And this is something that this guy, Barnes, that I just mentioned, it's called gyrochronology. Gyro for rotation, and chronology for time. And if it's valid for all of the late-type stars, if this idea is valid, then all you have to do is go out and measure the star's rotation period, and you can get an estimate of its age. Now again, with the Kepler, where we have rotation periods, and in particular, Kepler has observed several star clusters. We're back to the star clusters again. But we already know the ages of those star clusters from the other techniques. And so here are 2 star clusters. This is MGC 6811, the one I just showed you. And this is Messier 67, M67, which was observed in the K2 part of the project. And here are rotation periods versus color index temperature, basically here, along the main sequence. And you can see that in this, there's a very nice trend that you start here. These are late F spectral type stars. These stars do not have convective layers on their outer layers, so they don't spin down. So these stay rapid rotators. So the hotter stars don't follow this trend. It's only the cooler stars. And the sun is right, here's the sun right there. And so you see the sun has a 27-day period approximately. And so this one, the 1 billion-year-old star cluster, there's the trend. Over here, we have M67, which is 4 billion years old. And here's the sun again, so this is, I align these two figures so that the sun is across both of them. But you see the periods are much longer here. And so in a general sort of a way, it seems to work. There's quite a bit of scatter here. The error bars here are larger because they only spent 90 days looking at this, and so the rotation periods are not as accurate. And there's another problem as well. I'll come to that in a moment. But these were observed for a longer period of time. But it seems like it's going to work. But the problem is that these are, this is early K spectral type here, and they're not very, what about the smaller stars, the late K and M spectral type stars? Do they follow the same rule? By the time we get to the least massive stars, the M stars, are fully convective throughout the entire star. So their magnetic structure is somewhat different from the sun. They may rotate like as a solid body, in fact. And so the question of how the magnetic fields interact with rotation is probably quite different in the M stars. So we don't know this, and we can't see those stars in these clusters in the Kepler field, they're too faint. So can we find some of these stars somewhere else? And so I had an idea, and here's where it comes to my idea of all this, is to look at wide binary stars, again, in this Kepler field. And so here, if we find a star, a wide binary system where we have, say, a G-type star like the sun, and its companion maybe is a late K or an early M star, if it's really a physical binary, we would assume the two stars are the same age. We may not necessarily know what that age is, but we'd assume they have the same age. And then all we have to do is take my Kepler data for those stars and see what the rotation periods are. That was my idea. It seemed like a simple idea. So I had to try to find visual binary stars in the Kepler field of view. And if you look at the catalogs of visual binaries, I think you'll find 2 or 3 binary stars in the Kepler catalog, in that field of view. But there's probably lots and lots more that haven't been discovered, because they're fainter and so forth. So what I did was I went to that Gaia catalog, which has observed the same stars, and I cross-referenced the 2 catalogs, and I was able to, using the Gaia data and using proper motion and parallax data for those stars, I was able to identify 313 pairs of stars that had the same proper motion and the same parallax within small amounts. Presumably, those represent physical pairs. Here's this graph pictured here. So here's the difference in parallax on the left-hand side between the 2 stars. I just picked every pair of stars in the catalog. Okay, so I went through, which is a lot of pairs, but it's easy to do that. And so these are ones where there's a small difference, and this parallax difference, this I didn't. Oh yeah, here's the units here. These are units of milli-arc seconds. Okay, thousandths of an arc second. So the uncertainty of these measurements is about 2/100ths of an arc second, 20 micro arc seconds. Extraordinary precise angle. And here's the proper motion difference between these. Now, here's this bunch of stars here. They have the same parallax and the same proper motion within a very small degree. So I'm guessing that these are physical pairs. They're all, I should also point out, by the way, I took these pairs of stars only when they were moderately close together. Once I know the parallax, I know how far away the stars are, and so I can tell, and so I set a limit that the stars had to be within 50,000 astronomical units of one another, which is again something I can derive from the data. They also had to be, these had to be wide binaries. They couldn't be close binaries, because if they were too close together, the Kepler spacecraft couldn't resolve the two stars. So I had limits on both sides of that. Anyway, so I came up with this. Now, these stars here, a few of these actually are also probably true binary, but these are mostly not binaries. They have, again, a small parallax difference, and a pretty small proper motion difference. So what are these stars? Well, they're just random stars that happen to be very distant. If you have a distant star, two far away stars are going to have a small parallax difference. This is probably didn't do this right. I should have taken the actual physical difference, but never mind that. To test my thing here, on the right-hand side, I took each star that I went and took each star in turn as a target, and I took the star, and instead of comparing it with a nearby star, I compared it with a faraway star. There couldn't possibly be a binary star with that. Okay, so this is each of my target stars, each of the 200,000 stars in the Kepler field of view, compared with stars somewhere off somewhere else, a certain distance away. And you get these, but you don't see anything down here. Just a couple of stars here. So these are very high probability actual physical pairs. So that was my sample. I get a sidelight here. To get the rotation periods, here's a typical light curve from Kepler data for 4 years of data. There's 4 years of measurements crammed into that one figure. This is where I've subtracted the mean. So this is the mean value of that star. And then I've done a further adjustment to get unit variance. So this is the same data adjusted, so the variance is day, quarter by quarter. So there's each quarter of, each 3 months, the Kepler spacecraft took a series of measurements with the spacecraft. Then they had to rotate the spacecraft to get the solar panels lined up right. So the next quarter, the data was independent of the first quarter. And so I had to treat the separate quarters separately here. You do that, this is what I did. Or their Lone Scargill is a variation of a Fourier type of analysis of it. On one side of the star, it rotates around this side. Wow, maybe there's another star spot on that side. So you're going to get 2 peaks for every period of rotation. Maybe. I mean, in some cases you might. In fact, this is a bit of a problem because you don't necessarily know. So it could be that this is the real period, this one here, and this is something else. So there is an ambiguity in this. There's we have a possible period aliasing going on in this. But I concluded that this is the primary period of this one, about 19 days, and this is the period of this one, around 24 days. That's what I concluded for those 2 stars. So now I have the periods for the 2 stars, a hot one and a cool one. And so I thought up this. Well, now we take a look at this figure. Let's look at the top figure first. Not worry about the bottom one yet. So here's all of the periods for the individual stars of my 313 binary pairs. So these are just the individual stars. It's their period in days versus the color, the temperature. And here's the spectral type. So we start here at around anything hotter than this. These periods are not as a result. Well, they might be as a result of rotation, but not because of stellar activity anyway. There's other things that can be going on there. Some of these may be Delta Scuti stars, for example. Anyway, and as you see, as we get the cooler stars, we get longer and longer periods. Here's the sun, by the way, right here. And here is Sidney Barnes's model. This is a model of a 3 billion year old sequence of proposed stars, or rotation periods. And here's a model of a 1 billion year old isochron, geochron. And you can see in a general sort of a way, the patterns looks about right. But now when I connect the pairs of stars together, I get this awful mess. So here, for example, there's the hot star, and there's its cool companion. And there's another one that's cool companion. And sort of they go that way, but then we have some like, here's the hot one, there's the cool one, getting a shorter period. And there's even this sort of thing. And we have some stars here where its companions are way up here. So maybe this is where the reality hits the fake news or something like that. There's several possible things going on here. You remember the pictures I showed you with the star clusters look much cleaner than that. And there's probably several things going on here. So I spent quite a bit of time doing this and have come up with something like this. But let's see what might be happening here. First of all, there still is a possibility that some of those are unrelated pairs. I don't think there's very many there that way, but there may be a few. And there may also be this period aliasing problem. The true period may be either 1/2 or twice the measured period. Another possibility is, to affect things a little bit, is differential rotation. The sun, at different latitudes, of course we know, rotates with different speeds. So if you had a star spot at a high latitude in one of the stars of the pair, and at a low latitude in the other star, they wouldn't necessarily match up quite right. People have done more elaborate studies than I have with the same data, and actually have been able to deduce differential rotation in a few of these stars. So this is probably a significant factor in some cases. The other is that there may be something more complicated going on that we didn't see in those stars in the star clusters. One possibility is, first of all, I said there's an early stage where we have a magnetically highly active and rapid spin down. And then there's this sort of middle stage, which I'm calling the Skumanic stage here, where something like the T to the 1/2 power goes, which goes for quite a while. But as a star spins down, its magnetic field gets weaker, and the star spots get smaller, and the light variations get smaller. Eventually, you can't see, even with highly precise photometry, you cannot no longer see the star vary. But there may also be, at that point when the magnetic field is weak, there's also no longer a mechanism for the stellar wind to escape, and so there's no longer any driving force to carry away the angular momentum. So it may be that eventually the spin down stalls, you get an indetected period, and going back to the previous one, we don't see very many up here, only a little bit above the sun, you see, we don't see stars in this picture. Now, there are probably older stars than that in the galaxy, but I didn't get them, I wasn't able to find periods for them. But I should point out, by the way, that this is only about half of the binary stars that I found. The rest of them, I couldn't measure periods for. So we have that. Now, it's also possible that these late K and the early M stars might follow a different evolutionary path because they have much deeper convective layers. I might also, back to this figure, this is spectral type M0. Stars, there were very few of them in the Kepler field. Stars cooler than this, right about here, stars become fully convective, the late M stars. But there was only a very small number of those in the Kepler field of view. They were too faint. They didn't think about, when they were started the Kepler project, they weren't thinking of this stuff. So they didn't put them in their observing list. So we don't have anything there. None of the stars in mine are this fully convective late spectral M type stars. But there may still be something else going on here. Finally, and this may be a very important issue here, these are binary stars, wide binaries. How do you get a wide binary system in a galaxy? They probably don't start out that far apart. We have some kind of interaction, typically a three-body interaction, which very often leads to two stars close together in a close binary pair and one star way out. So all my wide binary, or many of my wide binaries, one or both of those stars may themselves have companions. And if those companions are close enough together, there will be tidal interactions between the two stars, and the rotation periods they get will have not very much to do with the spin down and gyrochronology. They'll have more to do with the orbital relationship of the two stars. This could be a major issue. Now, in those star clusters, they cheated. Well, not they cheated. But these stars were selected spectroscopically not to show spectroscopic radial velocity variations. So these are the good ones. And the ones I'm looking at are the messy ones, some of which have companions, I suppose. At any rate, so I think we have that problem. Now, so I think I've reached the end of the line with that particular gyrochronology business. I'm going to give up on that and go back to my other interests. And the question is, go back to my star clusters. And coming back now to the Gaia data, I haven't done any of this, but there are, and if you look at the catalogs of star clusters, of open clusters, there's a couple thousand of them that have been cataloged. These are ones, of course, that are observable in the optical from the sun. The whole galaxy is probably many times that, but we can't see them. But most of these star clusters have not, in the past they had to be observed one by one individually with telescopes on the Earth and on, avoiding cloudy nights and all that kind of stuff. So most of these stars, there's very little information on most of these clusters. There's very little information on them. But with Gaia, the situation is completely changed. We now have, in that Gaia catalog that exists, in so-called Data Release 2, DR2, all the optically visible star clusters we can see from here have data from which we can derive the distances to the cluster. From the parallax, we can get the parallax. We can get HR diagrams, color magnitude diagrams from the Gaia photometry, and we have the beginnings of the basis for doing a real comprehensive map or study of the system of star clusters in our galaxy, get their ages, supplementing with, and we can get to some degree, even with Gaia data, they can get some estimates of chemical composition and interstellar redding. But we can map out the, with using theoretical isochrones and possibly some ground-based measurements, we can map out some of these large-scale distributions of metallicity of ages and so forth in the galaxy. But there's also, I have a separate idea that maybe could be done. Even with Gaia, of course, we're still limited to a fairly small part of the galaxy because of interstellar absorption. But there's a few lines of sight in the galaxy where you can see right through the galaxy. And this is a favorite picture of mine. This is basically the Space Telescope Sky Survey. This is just a photographic atlas of the galaxy. Here's a galaxy at galactic latitude 0. So here we're looking right through the galactic plane, out beyond the galaxy to a distant galaxy. So we can see right through the galaxy in this area. And there's a fairly large area around there that we can see. The galactic plane, I guess, looks about like that through here. So we can see a slice of the galaxy, galactic disk here. And this seems to me to be would be a neat area using, again, starting at least from Gaia data, getting, mapping the compositions, the ages and so forth. And there's a number of star clusters also in the same direction. So I'm, working towards trying to see if I can get started with a project like that. Anyway, so let me summarize then, you can read my summary for me. So the key bottom line, of course, is that there really is enormous potential for doing astrophysics with a lot of these data sets. And of course, it's not just Gaia and the Kepler, but there's the ground-based surveys, the Sloan Digital Sky Survey, and there's the current new survey called TESS, a new satellite that's mapping bright stars in the galaxy from space, and other surveys. And Kepler project, as I said, is given all these sort of things. And the analysis of the Gaia data is really only just beginning. The people are mapping that, are mining that Gaia data like crazy right now, all around the world. I just went to an American Astronomical Society meeting a couple of weeks ago, and there was probably 100 papers at that meeting about Gaia data, even though the data came out only 8 months ago. And so it's an enormous thing here. And as far as the gyrochronology, of course, there's probably still some good astrophysics to learn about the rotations and about the magnetic fields. Of course, there's a lot one can learn from that. But in terms of large-scale finding of ages of stars,